All right, welcome everyone to today's seminar. Today we have Jesper Gjerloev, who is going to be speaking with us about the EZIE, the Electrojet Zeeman Imaging Explorer mission, as the EZIE project scientist. Jesper is currently at APL. He initially got his PhD from the Technical University of Denmark in 1997, and then moved to Goddard, where he continued to work on magnetospheronosphere coupling and field line currents, which he's going to be speaking with us about today. From Goddard, he moved from the University of Bergen as a professor and now holds an adjunct position at the University of Bergen. At APL, he is also the PI of the SuperMag project, and so I'm delighted to have him with us today to talk about EZIE. Jesper, if you'd like to take it away.
Thank you. I hope you guys can not only see my view graph, but hear me.
Yep, good to go.
Thank you. I think I have about 45 minutes, and I really am super grateful for you guys to spend time today to hear this. And my suggestion is that we go through it and you keep your questions until the end. So I'm sure I can get through everything. I hope that's okay. And maybe Kyle, you can moderate at the end too, if there's questions in the chat and so on. So thank you again for inviting me here today. Let me first and foremost say that my name is here, but there is a plus the entire EZIE team. I cannot overemphasize the importance of a team. A satellite mission is perhaps one of the most humbling exercises you will ever go through. You may think that you know a lot, but once you get involved in a mission, you realize that you're only one wheel in a big machine. It takes engineers and managers and costing experts and outreach people and what have you. And pretty soon you realize that even for a smaller mission in the MOO class mission of opportunity, a $60 million class, it still takes literally hundreds of people to put it together. And you'll be quite amazed by how capable people are. So again, thanks to the entire team. This is something that I think is really, really cool. And I frankly think we won this mission because it's really, really innovative and cool. And I hope I get that across. But I hope another thing comes across, which is you are welcome. You are welcome to join us. Contact me. There's all sorts of ways of being involved and being part of the mission. And all it takes is for you to reach out, and we will do whatever we can. And at the end of the talk here, I'll show you an example of all of that. So, okay, thank you. So first, part one, what on earth is this just at a glance? You can probably see the background here. It's 3 satellites that each look down with beams. They essentially have a 1 pixel camera looking down. It only looks at one wavelength, 118 gigahertz. It takes a spectra around that wavelength. And the emission comes from an oxygen layer at around 80 to 85 kilometers. So the EZIE here, we are trying to resolve decade-old questions that are associated with the auroral electrojets, equatorial, as well as the auroral electrojet. And again, we will take multi-point measurements with 3 spacecrafts and 4 points each, all taken simultaneously. We do this because it's a universal question. Actually, any magnetized body in the universe will interact with the surrounding space. And part of that is a flow of energy and particles, and currents play a key role in that interaction. In terms of the practicality in our society, these interactions and the currents are a key part of space weather. It affects satellite communication, what have you, all sorts of parts in our society. The science is also in the old decadal report, it was highlighted. And the mission we will launch in October, so we are getting close. We are ready, and it will go up on a SpaceX launch with a window opening October 1st. So let me just go back to this and focus on just the first part, the science part, because after all, we are all physicists, so we're excited about that part. So let's just focus on that. So EZIE has 2 basic science questions, and the way we structured the science story is that we had, again, well-defined science objectives with testable hypotheses. So the first one has to do with the substorm current, which the most often occurring large-scale phenomena in the magnetosphere-ionosphere system. And what is the basic current configuration associated with that process? We basically split it up into 3 hypotheses and with some other ones, but they can be simplified as you see to the right there, and I will go into much more detail about it. The second one is the latest, greatest, cool thing in our field, which is that no, there's no large-scale current system. It's just a bunch of little systems that are superposed on top of each other, next to each other. They look like a big system. I will focus on the first part here, the first science question, but I will get back to the second one a little bit later, so just be patient. This actually was revisited. You may think that the substorm current, which we all grew up with that in textbooks and so on, and you thought maybe this is dealt with and it's settled and all that. But Larry Kepko had an EZIE team with, as you see, a bunch of co-authors here some years ago, and they wrote a paper in which they essentially concluded that this is not a resolved problem. And that's why EZIE, to some extent, is launching to resolve this issue. I will only focus on the center one here, because that's the one I'm an author of. So I may want to tell the background. Where is this coming from? It's all good with the textbook, but when I wrote my thesis, my results didn't really fit into the single wedge system at the top, which is a substorm current wedge. I just couldn't squeeze or pull or whatever I did into that box of a single system. And we then spent, Hoffman and I spent the next, I don't know, 10, 12 years or something, 15 years, writing a long string of papers, trying to address different parts of that puzzle. And I will walk you through those parts, the things we were confused about. So let's just go back here one step and remind ourselves, what is a substorm? A substorm is essentially magnetosphere unloading energy into the ionosphere. It leads to this auroral display here, as you see the orange light here, but it also has currents associated with this. So on ground, you see all the ground magnetometers, little vectors there wiggling as the currents are evolving. And when you see this movie from one very simple, not simple, but a classical substorm, I think a couple of things should come to mind. One is that there certainly is a global morphology or behavior of them. This is a typical one. You can find many examples looking just the same. But you also see there's a lot of structure in different electrodynamic parameters. Here we got 2, the emissions and the ground magnetic field, right? And they seem to be correlated. If you see the light moving poleward, you see also the vectors starting moving coherently with that behavior. You can see spatially and temporally, it's very well correlated. So it certainly is a hint here. So this is the problem we're really trying to solve and trying to understand. What is the basic current configuration associated with that? Not the little stuff, but the big stuff, you know. Okay, so now we have a little bit of an intro. We have these 3 satellites trying to resolve this and differentiate between these 3 models at the top right corner. Which one could it be, right? But perhaps we need to step a little bit back and say, what on earth? Why did we even question the substorm current wedge solution of McPherson, the beautiful study of his from 73? Where is this coming from? So just bear with me and my own confusion about the entire field here. So this is part of my thesis way back. We built this on the Fuji beautiful and idea that actually the electrodynamics is organized by the emissions. So don't use MLT or magnetic local time or magnetic latitude or whatever reference frame you prefer. No, look at the emissions. So, and when you do that, you relate the measurements you make, the wiggles you make in the field or the particles, and you'd say, hey, you know what, this was just to the east of this feature or to the west of that feature. So here's an example of a Dynamics Explorer 2 image, and then you have one image and Dynamics Explorer 2 superposed pass onto that image. So you can see, for example, here to the right, I hope you can see my cursor. That is certainly to the west of this big blob, which is the substorm current or the westward traveling surge here ahead. So now you organize it that way. Well, if we do that, we can start seeing key features, and we can define some kind of a generic overall reference frame and saying, oh, okay, we have the search horn, and so on and so forth. We can identify these features. And that means that we can take all the individual events that are not the same and individual passes from different events. And we say, you know what, this was to the right of this feature, it was to the left of this feature, what have you. And then we can all combine the measurements and produce some kind of a map of whatever parameter we like. So that's the basic idea. I personally think it's tremendously strong, and it's quite beautiful. So we did that with all these passes based on this approach and these ideas. I think 32 satellite passes, and I calculated conductances as part of my thesis. And I had, for example, the Hall conductance, and I can do a little map of the Hall conductance for this particular one. But I also realized we also have convection electric field. And why don't we just combine the two? And voila, we have the Hall currents, right? And then vice versa, we can do that with the Peterson current, Joule heating, and field line currents, and what have you, the different ones. We have the full solution in principle. So once you do that, you end up with a map here. And then I looked at this map, and this is when my confusion basically started. I didn't get it. What on earth is this telling us? So let's see, for one, what are the findings from this particular study? Well, if you look at the electric jet post-midnight, it's centered somewhere around 65-ish or 66 degrees magnetic latitude. And pre-midnight, it seems to be closer to 69 or something. So there is a little bit of a kink here. Okay, and that's actually been seen by many other papers, so there's not much to talk about. It's in agreement with many other papers that use different techniques. So there is some kind of a polar kink there in the midnight region. If you look at the current in the pre-midnight region, there's an intensification from midnight towards the search head. We can figure out what is actually causing. We can zoom in on it and say, what is the electric jet strength here? Here's the electric jet integrated strength. It maximizes, it's negative, but it maximizes in strength at around 21. And then it basically is drained by upward field line currents. So here you see a map of the upward field line currents and the downward field line currents. This is the region 0 that feeds this part of the substorm current wedge. And it's drained by region 1, actually what they call region 1 high, or the most polar part of that. But it could be fed too by the meridional currents, and they're indicated here, but they're not much. There's a little bit of feeding in maybe the just 19 to 21 or something region, but not much afterwards. So it really is fed by an imbalance between this region 0 and region 1 field line currents. So there is an imbalance. It's being fed near midnight here. You only feed 60 from the post-midnight, and then you basically pump in current, you maximize around 21, and then you drain it by upward field line currents here. So that's basically the basic system that we see. We don't have a good balance between, if you take the total current post-midnight and pre-midnight, they don't match. You can calculate this in different ways, but you're going to end up with the same result. Hang on, let me just move this window here. The harangue region, this is actually of importance. We didn't find this to be a harangue discontinuity per se. There's a wide region, it gets wider towards midnight, and this has importance because this current post-midnight will flow straight in towards this region of very, very low convection. How is it going to be? How is it going to be maintained, the current? So that has also been seen by Proven et al. They found and concluded that they have a very low convection region here. This is from superdown measurements. So where the convection for some reason is suppressed. So following up and just looking at it individual passes, sometimes I always get nervous. You get these statistical averages, and that's all good. We're all happy. But to what extent does that reproduce in single events, or is there some kind of smearing going on? So let's just look at individual events here. This again is after Fuji. If we look at all these passes post-midnight, the convection and the particle precipitation essentially leads to a large wide electrojet flowing, westward electrojet. There really is no eastward electric jet here. It's one big wide westward electric jet flowing across towards midnight. If we take a pre-midnight pass, what is the Fuji called the middle surge, what they found, or what we see is that we have very strong convection. It's structured and so on, but it's very strong. But it's also overlapping with very intense electron precipitation that leads to very high conductances. You can have conductances of 100 there most in the Hall conductances. So you have very strong electric field, and you got very strong or high conductance, and that leads to a very intense current. But if you notice where it's located, it's just located inside the open closed field line. It's not across the entire bunch. And if you see just a little bit equator what here, you have that region, I hope you can see my cursor, a very low convection. And that's what we call the harangue region. So even you got particle precipitation, you have very little convection. But again, polar of that, you have a region of very strong convection associated with high conductances. If we move over to the surge itself, we see the same. It's somewhat narrower, but again, very intense convection. We call it a convection spike. And that is associated with, again, an inverted V here, which leads to very high conductances. So the same basic picture. And again, look at the convection equator, what of that? It goes pancake flat, right? So, which is what we call, again, the harangue region. Okay, so we moved on and said, okay, why don't we look at the ground magnetometers? And Hoffman and we looked at it, and we realized, you know what? It's nice with Greenland magnetometers, but we need charisma. Well, we also need Scandinavia. Well, we also need Alaska, and it kept going like that. Because we realized to address some of these issues, we need global and continuous coverage, global and continuous. And as we did that, putting all these maps together, we need to rotate them to get the same coordinate system. We need to baseline them. We need to sort all these issues out. And that actually led to SuperMag. So with SuperMag, it was a little bit easier. It's all taken care of, so to speak. But we used 116 isolated substorms that were carefully picked by a number of objective, I guess, criteria. And this is the pattern we got near peak. And again, you see this poleward kink, westward electric jet, and the poleward kink and the pre-midnight part here. But we also saw another feature. If you look at this polar cap swirl is what we called it. It's actually a characteristic feature that you can see repeated every single time you have a substorm current wedge and a typical substorm. That's a polar cap swirl. So we added to the Dynamics Explorer findings that we essentially supported. We found something new that we had to add to the list. And that led us to ask one question. For these 116 events, how many of them actually agree with this average pattern? Do they all show the same? Maybe not the same intensity, but for example, post-midnight, if the average says this is a westward electric jet, do they all agree with that? What is the spread in the individual ones? And we made this little plot here, color-coded. One or yellow means that all the individual events agree. Black means it's all over the place. They point in all sorts of directions. This is not a magnitude, as you see. We take the magnitude out. We're only looking at directions or orientations. So one substorm might be stronger than the others. We don't care. What we do care is the basic pattern. Is the pattern the same? So this is the pattern we got out. And it's actually quite beautiful if you think of it, because here's the westward electric jet post-midnight. It's essentially all of them show the same pattern. We have a pre-midnight here. We have feeding and drainage here. I'll get to that in a second. And voila, you have very poor correlation right here, the poleward of that westward electric jet inside the polar cap. And why is that? Well, think about the polar cap swirl here. This is basically very low, and that means that if you just shift things a little bit to left and right, up or down, or whatever you do, if you just slush things slightly, the center here will lead to essentially no correlation. The vectors will go in all directions as you do, and that's what's causing this blackness here, or the very poor correlation. In here you have nothing, but the polar cap swirl is explaining that quite nicely. If we look at the harangue here, we can see the harangue actually going through it. That made us quite happy. If we can get very poor correlation here, if it just shift a little bit, then I think our normalization process and organization is really doing a good job, right? We're not smearing out the features, so we can recognize it. If we zoom out a little bit, just go to lower latitudes, because we want to look at the feeding and drainage. We're like, okay, this is wonderful. They all have drainage near the surge head. They tend to all have some kind of maybe distributed, but some feeding post midnight. And then we had a problem, because what on earth is that stuff? This is subaurora, and it says nothing. What on earth? How can you have consistent feeding post midnight, consistent drainage pre-midnight, and somehow you have very poor correlation in the midnight region there? If you had just feeding and drainage, and they're highly correlated, the signal in midnight by definition is highly correlated, and yet we get black. It's all over the place, and that confused us. So that was something to take to heart, where observations may not agree with what you have, your preconceived notion is. So sometimes we just got to listen. So, okay. So that's what, and actually, if you go back to this and you go back to the original papers, beautiful, beautiful papers. I love those papers by McFerrin. And you look at the model here and the data, and just notice that the dotted is reversed between the model and the data here. Somehow it is, so the solid below in data is the dotted above. But if you look at these carefully, you find that perhaps this is an idealistic picture, but maybe nature does not necessarily agree. You can argue here that we don't have great coverage with the ground max, and that's why you can argue that maybe things are shifted around, and you can argue different ways. But again, the other option is, of course, that maybe this simplistic model does not tell the full story. So that's another option. So, but I just want to point out that even if you go back to the original papers, you may have some questions about some of this interpretation. So we went on again. We did not stop with the Dynamics Explorer and the SuperMag approach to this problem. We looked at just the emissions. These are polar emissions. And what we looked at is, again, for these 116 substorm, we looked at imaging, and we came up, after normalized and so on and so forth, came up with a typical evolution in the emissions. This is as a function of MLT, so magnetic local time, and you have latitude up each. And the first, this is prior to onset. Then you have the onset. You can probably identify that. The poleward expansion, we got into the peak, and then the recovery phase below. And the reason we did that is, again, you can view a substorm from different electrodynamic parameters. We looked at the ground max, we looked at convection and so on above, as well as currents. And now we're looking at the emissions here. We have it available. So let's see what they're telling us in terms of the story here. Okay, so when we looked at this, we said, wait a second, we can actually do a simplistic separation. If you have the oval itself and you have some kind of a superposed process on top, maybe we can separate these by simple Gaussian. So we have fit a double Gaussian fit to each of these MLT sectors, and then we construct that. And what that allows us is to separate into what we call the oval aurora. It's the oval itself, as well as the, hang on a second, as well as the auroral bulge. And if you look at these, our double Gaussian fit and the data themselves, they reproduce tremendously well with this simple approach. But it does something. It allows us to, again, perhaps separate a process that is superposed onto a background oval. And then we can see how they individually evolve. The oval aurora, as you see, it intensifies, but it doesn't really move at all. The bulge itself starts quite weak and within the oval, and then it moves poleward very, very fast, and it intensifies. So you have a completely different temporal behavior of these two different components. So this is perhaps a way to separate, again, components that make up what you see. The other thing that struck us is that if you just look at the images, here's the original Fuji picture at the top that we saw earlier. you see that again we have the surge head that we all love. It's been studied extensively, but you got some emissions here in the mid-90s region. You also have a big blob. It has received almost no attention. If you look at polar below, you see the same, again, the surge head, and again, these emissions here. And it's kind of obvious to say, wait a second, what's going on? And then argue, this may be associated with drainage of the westward electric jet. So this is one interpretation. When I presented this at GEM last summer, Mike Henderson made a wonderful comment and said, wait a second, this could be a streamer. So I actually went back and I said, well, good point. I don't think that is really the issue. Generally, it might sometimes be the issue. There's also a temporal issue here going on, but sometimes, so I went back to these 116 substorms, and in some cases, I think you can probably argue that maybe this is associated with the streamer, this midnight, but it is certainly not every time. And sometimes you got to provide another explanation. But it was a great comment. So the implied findings here, again, it's implied because we all know the Sukhanenko modeling is very, very difficult. So I actually asked Sukhanenko about the interpretation here, and I'll get back to that in a second. But if we just simplistically have a feeding post-midnight and some kind of a current flowing around and a drainage, then this actually, regardless of which KP model you use, will be more of a long tail than a cross tail current. So the idea in the original picture is that we somehow diverge across the cross tail current into the ionosphere and back out. But that doesn't really match this. So I asked Sukhanenko, is it possible that the skewing here, that this doesn't really apply very well? Is it possible that this long tail closure really is just because of an incorrect mapping? And his argument was that the pre-midnight part should map further down the tail. And in his model, the distortion is the other way. So it's probably, according to him, it should be more long tail than this. So that we have a problem. So when we introduced a drainage and a feeding near midnight, so these are separate parts, we find that it is much more cross tail, but we got an inner loop now of the current. So this is a two-loop solution, so to speak. So we went on to say, why on earth? Why has this not been seen from ground max? I mean, this should be obvious, right? So we did a simple biosavar. We put in these fairly simple model wire models, and you can see how the current flows below in the left one. The current flows westward electric jet, and then it somehow links up poleward into a pre-midnight part, and which is drained. In the one to the right, we have a post-midnight that is drained by current in midnight. Everything is latitudinal, and you have a pre-midnight part that is fed around midnight and flows straight across. Conceptually, they're very different, but if you look at the ground perturbation produced by these, you will find that they actually are tremendously similar. The ground perturbations is almost impossible from a given event to see. But there is one part perhaps worth noticing, which is that if you look at the polar cap, you have these perturbations sticking up around 21 towards the pole, but they don't really come down. In the two-wedge solution, you see again the same. They move point poleward at 21, and then around midnight they point equatorward. So we create this polar cap swirl, and that's because you have a feeding just around midnight in this big red blob there. So if we take all these different studies, I don't know how many papers we wrote, and kind of combined all these findings and say, hey, does it match these models? I think for the single wedge solution, the poleward king, you need some modification. I'm not completely sure how. The intensification of the current from midnight to the surge head, we seem to have a conflict, and the difference in total current, we need to have a conflict. The ring region, I think some modification is needed, but maybe not very important. The polar cap swirl, we have some conflict. The poor correlation, just midnight, just subarachnoidal, I don't understand how you can do that with a single wedge. The two oval components, separation and the emissions, why are the temporary behavior so different between the pre-midnight and the post-midnight? The divergence of the electrojet, I think we may have to go back to Mike Henderson and convince him. And the cross-tail current divergence, I don't know. It's how much you actually believe these mapping and so on. But of course, to the right, there is no conflict because it's designed to have no conflict. So perhaps this list is slightly unfair. But again, we designed it as such that it was in agreement with all these observations. So, okay. So the question is, of course, and I've shown this before, but I'll show it again to those who haven't seen it. I tried to conceptually understand why we could come up with a different solution than the previous solution. And it reminded me of the cathedral in Sevilla. It's quite extraordinary. And if you go to Sevilla, please go in and see it. You'll see gold and beautiful windows and what have you, glass mosaics and so on. But you can also look at the floor, and you can see this beautiful star in the floor. I guess the granite and marble here is laid in. It's quite beautiful, and I took a picture of it. And then I looked up, and I realized, nope, it's not a star. It's actually squares. So from the local measurements, I made one conclusion. And if I looked globally and had much better coverage, I came to a completely different conclusion. And you can see the star there. It is indeed the same floor. So the interpretation, I think, was just incorrect, frankly. Okay. So let's move to part 3. I think we are right on time here. So this is a magnetic mission, but we don't have a magnetometer, which is kind of a cool concept, right? So, but it's also multi-point measurements, both separated in space and time. So it allows us to separate space and time, variations in space and time, which is, of course, a very strong thing in our field. But we need to step back. And for those who are not super duper familiar with everything in our field, I just want to step way back. We have the sun here to the left. We got the solar wind. It interacts with the Earth magnetic field, which creates this big void, which is the magnetosphere. And that's where essentially the Earth, I would call it, where the Earth and the Earth magnetic field is dominating what is going on. The solar wind is diverted around, but of course we have the interactions. Everybody knows this model or this figure. It's from any textbook. And it tells us it's quite a nice and organized. But if we do global MHD simulations, this is from Slav American, has provided me this. You see all sorts of structures and flows and what have you. And it's highly dynamic and structured. And we are saying, wait a second, right? How on earth are we going to understand this? So there is one way. This is what EZIE is saying. We are saying in this very simplistic, horrible figure. I apologize for that. That if we look at the aurora electrojet and make the key measurement of the aurora electrojet part, and there is indeed a large-scale current system, then just by looking at how this aurora electrojet is organized, structured, and how it's evolving, we can put constraints on the entire massive current system flowing over 100,000 miles into space. So again, local measurements of the aurora electrojet provides constraints to the global magnetospheric evolution and structure. So that is the idea. And here is a global MHD simulation to the right again. Right now, it's southward IMF, and you see these wiggly lines, the purple lines, they start moving toward Earth here. Now, whoop, this is the dipolarizations. The energy was unloaded. Here we start, boom, we hit the magnetosphere. We start loading, you stretch all these thin lines out as you load energy into the magnetosphere. You start having all these flow channels. Now it's as stretched as it can be, and voila, boom, it hits in. So we have this loading, unloading cycle, and you can see how that's associated with the wiggly purple lines there. As they stretch, is part of the loading of the energy into the magnetosphere and the subsequent unloading. And if we then look to the left here, and we look at simulations here of EZIE, as we flew through these global MHDs and see what we will measure, we see the 4 beams here going over Iceland, and the red and purple is the magnetic field, and the little vectors are the currents, the equivalent current. We can see over Greenland here, we can see that we can actually derive what the structure of the electrojet system is. And by taking the next spacecraft, we can see, okay, we can make a map with the first. The next one comes back 10 minutes later, or 5 minutes later, what have you. And voila, we can see how this map has evolved over that time. Okay, so that's the idea. Again, we have no magnetometer, but the electrojet flows at around 100, 110 kilometers in that region. And that presents a real difficult problem. You can look at them from magnetometers on ground, but they're located some 100 kilometers away, so there's a vast amount of smearing going on. But of course, the beautiful thing is that they're continuous. They just keep making measurements, and you have a lot of them. And if something breaks, you can go out to the shed and fix it, right? So it's doable. The other one is you can do a rocket. You can get very precise in situ measurement, but you go up through it, and then you come down through it. So that's perhaps important if you want to study that event. And of course, rockets are a tremendously strong asset, but it also has disadvantages. Or you can use a satellite at some, but that's typically even 400, 500, 600 kilometers up, which leads to even more smearing. So even if you have a very precise measurement, you cannot avoid the smearing, which is simply a function of the distance. What we are taking advantage of is that there's an O2 emissions taking place around 80, 85 kilometers. And by looking down at those emissions and making a very careful spectra, we can look at the Siemens split due to that. And that essentially allows us to make a vector measurement of the magnetic field right at the emission layer. The advantage is here that we are very, very close. So here's one from Kalalaunda's beautiful paper. And what you should pay attention to is that on ground, things tend to be smoothed out. It's much more smooth. And when you move to 85 kilometer, 80, suddenly you see much finer scales to structure. But you also get a much stronger signal. Rule of thumb is about 70% you gain. So in other words, if you have 400 nanotesla typical substorm on ground, at the altitude of the emissions, you get about 700 nanotesla. So you get a stronger signal, you get a finer structure by making these measurements. Okay, so going back very, very briefly here, again, since that substorm current, which as I alluded to, there's been many papers making different kind of suggestions. And here's just 6 of them. And you realize that perhaps, and that's what we did in the proposal, we said, you know what, they actually organize themselves in 3 groups. And we can make a simplistic picture of what that current system should be in each of these groups or categories of solutions. And that, of course, if you notice, they all provide a feeding pre-midnight and a drainage post-midnight, but it's right in the midnight region where the smoking gun is. That's where these models differ. That's where they don't agree. So we don't fly through the search head or the feeding post-midnight because nobody cares, frankly. What we do fly through is right that question mark. So that's what EZIE is doing. It's making all its measurement event after event in right that region, and that allows us to constrain and say it's model A, B, or C, or maybe none of the above. Who knows? So that's what we're doing. So we have designed it very carefully to get the necessary measurement in the key region at the right time. Okay, there's a second question, and I won't go into it too much, but this has received a lot of attention and people love it. And essentially it says that no, you don't have a large-scale system. Here's Sergeyev's beautiful paper, but it could be any of the other ones. It says, no, you have a bunch of little wedgelets, and global MHD tends to support this. So it's quite beautiful with a cause in the magnetosphere and effect in the ionosphere. This cause and effect, and it's very appealing. And you can see these streamers. The problem with appealing pictures is that I'm not sure nature finds them the same, equally appealing. Maybe nature disagrees. So even just because we think it looks nice, we need to ask and look at observations. So EZIE is designed to make the measurements with the spatial resolution and the temporal evolution here, the separation between the spacecraft to test, is it the dynamic wedgelets where they're much more structured, or is it the large scale, which is much more constant and slowly varying and larger scales. So, of course, you could ask, who cares? This may be a nice scientific question, but does it matter? And here's an argument for why it matters. In the large-scale system, in these two waterfalls, the amount of water provided in the waterfalls is the same. In the magnetospheric sense, it's the energy provided from the magnetosphere to the ionosphere. But the amount of water is the same if you integrate over space and time. You just wait and measure. But to the left, you have a very laminar, organized, constant flow. It's rather stable. And to the right, it's very sporadic and localized. And the impact on the atmosphere and our society is completely, utterly different. The one on the right has profound impact on our society and systems because it is highly variable and highly structured. While again, the left one is much more laminar and slow. So again, they say the same amount of energy is transported, but again, the impact and the way it is being is very, very different. Okay, so does it work? We are doing this kind of very special way of making the measurements, and I think you should ask, does this work at all? And we have beaten this to death, and we are still doing it. But of course, once we get the measurements, I think everybody will be convinced. The way we saw it is we have, again, these three spacecraft. They look down 4 beams. We published a paper where we showed that we can, a proof of concept paper, where we can use these emissions to get a spectra, separate them, and get the polarization and so on. And that allows us to derive a magnetic field. From these magnetic fields, the vector field, with all the noise included and so on, we can then do the inversions and we cover the current that produced that magnetic field. And we don't have the first part, of course, because we're not flying yet. We will launch in October. But what we can do is we can replace those 3 spacecraft with a global MHD. It's as good as it gets. And Slava American did this for us. So here we fly through this particular region. And then we take the ground truth here provided by a global MHD, run it through completely realistic noise and attitude and what have you, uncertainties in the measurements, and we can derive this pattern to the right. And I think for the purpose of us answering the science questions as they were stated, you can see the input and the output. It's very, very equivalent. And in fact, the latest, greatest noise numbers that we have gotten are better than we even hoped for. So this will work exceedingly well. It was all published, so we have a good handle on how this is working. Part 5, we want to work with you. You are welcome. So all you got to do is contact us, and we can perhaps put some ideas about behind this. We have an outreach component with where we deploy about 700 magnetometers. These are little kits it's to schools, 700 schools around the US and in Canada. We have made it very, very user-friendly. A middle schooler to high schooler can put it together. It's like Lego. I come from the country of Lego, so it has to be like Lego. You put it together and you deploy it. And you can look at your phone, you can look at your computer, whatever, to see what the magnetic field is doing in your backyard. And again, it is primarily for education, but the question, of course, to somebody, a nerd like me, is how good can we make it? How good can it really be? But again, you get a cool box. There's no manual, because the entire concept of a manual, I hate that. I don't want to read a manual. It needs to be on an app or something cool like that. And here is what it looks like. This is an earlier version, but it's close. Here, it's like a little lunchbox. Here's to scale. We use an Oreo cookie because we all like Oreo cookies. At least I do. So this is what it looks. It's a whole suite of a bunch of instruments, GPS, accelerometer, gyro, what have you, temperature measurements. And it looks like this. Why should it be black? An instrument doesn't work better if it looks nerdy. So here you got it in cool looking greenish, bluish, but you can also get it in gold, or you can get sparkles if you want, because we should not be so elitist. We should be inclusive, and I like very much that things should be fun. It doesn't do better science to be nerdy. Okay, so once you deliver the data, it runs through all this. There's a massive package of post-processing. that is to some extent based on the SuperMag. Nobody needs to do all this. You can do it yourself. And here is uncalibrated data from Robin Barnes' backyard. So here is in the middle panel. The top one is KP, just to show what is going on. Here is the middle panel. At the bottom, you have a USGS magnetometer in Fredericksburg. And I think you can probably convince yourself pretty fast that it is strong. But in Alaska, Dogakan and her group did 2 students. They put it out and compared with the EZIE magnetometer, and here's what they did after a brief calibration. Again, this is still preliminary, but again, I think it certainly is strong enough to do science. So here's a movie.
Auroras, or northern and southern lights, have fascinated people for millennia.
Can you hear that, Kyle?
Yep. Yeah, the sound comes through.
Have formed traditions around these mysterious dancing lights in the sky. But hidden within them are secrets of the link between Earth and the sun. A link that scientists want to better understand so they can predict and therefore protect our technology from the dangers of space. Particles and energy from the sun interact with invisible electric currents in Earth's atmosphere, creating dazzling aurora light shows. But if strong enough, they can also disrupt GPS satellites, communication systems, and power grids on the ground. To study these electrical currents, NASA is launching EZIE in 2024. The mission will put 3 small satellites in orbit around Earth to create maps of these electrical currents for the first time. And you can help. Learners can join our team by becoming citizen scientists who collect data over time, helping protect our technology from the hazards of space weather. What's a citizen scientist? They are members of the public, like you, who collaborate with professional scientists by helping collect data about our world. And they make a big impact. Intimidated? Don't be. Our EZIE Magnetometer Maker Kit provides everything you need to participate and can be used by learners of all ages. Just like a professional engineer, you will build an instrument to collect valuable information about the world around you over the course of a year. Don't worry, technical support is available if you need it. Your data will provide essential context for the measurements that EZIE satellites are making high above, helping them map the electrical currents. Educational activities and design challenges, which we provide, will help learners make EZIE-Mag their own. Learners will be able to connect with EZIE researchers through interactive webinars and even connect with each other through our global Pen Pal program. Possibilities for meaningful learning are endless. Now it's your turn. Reach out to learn more about joining the EZIE-Mag community and helping scientists protect our technology and our planet.
So perhaps some of you noticed that you will be part of, and in fact, we have a JGR paper, quite beautiful, written by a student called Michael Madier. It's actually really beautiful, where he showed that if you take our patterns, our equivalent current solutions, and you include a ground magnetometer somewhere in that pattern, you actually get a better solution. So in other words, these mags, of course, scientific mags even more, but these 2 with feedback, and we can provide a high-level product of solutions where that is included. So you are literally a part of it. So thank you so much for paying attention, and I hope it makes sense, and you can ask me anything essentially, but most importantly, you are welcome if you want to work with us. Always feel free to give me a call or send me an email. Thank you.
Thank you, Jesper, for a really cool talk. Those lunchbox magnetometers are super cool. So we have a comment from
$200.
Pardon?
$200 all inclusive.
That's really interesting. So I have a comment, or I have a question about that. Do you think they can be used as scientific caliber? The plots that you showed that they were very, very similar.
So the way I see it is with everything, you need to be careful, right? So it depends upon what your science objective is. But if you look at MI system physics, typically that's fairly, certainly in Aurora, but even at latitudes here in my backyard here, the signal to noise is fine, and you will do exceedingly well. If you're interested in 1 second resolution, a fine structure, you may not do well, right? But it is not a replacement for scientific magnetometers, but it is a contribution. And my best example to that is we're all excited about GICs and, for space weather and so on. But GICs, the impact is highly correlated with the ground conductivity below. And for that you can have very high gradients over a matter of kilometers. And for that, to capture that kind of structure, you need a very dense network of magnetometers. And for that, it's hard to envision that you can deploy 10,000 science mag at the cost of 100,000 each. Mm-hmm. But maybe, so the way I view them is that they are an addition. It's a little bit like a CubeSat cannot necessarily replace a full-blown science satellite, but it can contribute too. So that's the way I see it. I think, I have a whole story behind that. But anyway, so that was my short answer. Does that make sense?
No, yeah, perfectly. I think with GICs, some things where you don't need the, kind of sub-nanotesla resolution, they would work really well for. And I see that you're using a Raspberry Pi. So you guys thinking possibly using SIM cards to download data for that then?
So there's two ways to get the data. It has a little flash memory card in it that holds data for whatever. It's ridiculous amount of time, right? But all the software is such that you just download it and install it. It's very, very simple. Again, a middle schooler can do it. So you basically does that, then it leaves you with three options. You can check the SIM card out and read that, but that of course disturbs your measurements. Two, you can use your computer and just with the web browser, it packs automatically daily and weekly files, zip files, so you just download them using a web browser on your phone or your iPad or your computer, whatever you like. You can log into the Mac. Or the third option is that you automatically it tells it to using your Wi-Fi to upload the data automatically to our server. It's whatever you want.
Very cool. So we do have one comment from Witham Reeve. He says that he is particularly interested in the Electrojets as he lives in Anchorage, just right below them. So I think you guys are going to get a lot of traction with this. The substorm current wedge is a really interesting phenomena, and as you've shown, it is still, under a lot of debate as to how currents are closed, and I think this will contribute a lot to MI coupling. So thank you very much.
Thank you, and William, thank you for your comment. You do wonderful work with the SAM, so it's really wonderful. Thank you for your comment.
So thank you everyone for attending today. Our next seminar will be next Monday at noon, and Ian Mann will be talking about the Radicals mission, the small satellite precipitation mission from Canada, the U of A and the U of C. So I hope to see everyone next week. Thanks again, Jesper.
Thank you so much.
Thanks, Jesper. Bye-bye.
Thank you, guys. Thank you.